How to summarize, in your opinion? This drama of fermion masses and mixings. You know, it's often sort of claimed to be a kind of problem in the Standard Model, the Xerox copies of our families. After all, the world is made just out of up and down quark and the electron. You may ask what the neutrinos are doing there. Do you know what they are doing in the universe? I mean, what does the universe consist of? Let's make a little digression, a few minutes, and bridge the gap with the cosmology class. It's made out of stars and planets. Well, that's proton, neutron, and the electron. Then, that's just a minor. There are almost no stars in the universe, if you think of that, okay? The number of baryons, as we call them, and charged leptons is basically zero, because most of the universe is in the form of background radiation, the photons. Do you know the ratio, roughly? It's an interesting number between the two densities of the numbers. How many more photons then? You didn't talk about it yet.
Million.
Okay, let's leave it then for Paolo.
Can we know this from the black body radiation of the universe?
Well, you have to know also how many stars there are. If you want to know the ratio, you have to know both. Of course you can. Well, now that you ask, how would you know? How do you know from the radiation? What do you know about the background radiation?
Temperature.
Once you know the temperature, you know everything. Remember, that's the only parameter that matters when you have radiation. And the density, for example, this is what you want, is given by? Even if you know nothing, dimensions will tell you that it has to be TQ. So if you know the temperature, the density has dimension of mass is Q, right? So this is the density of photons. And that's about 3 degrees Kelvin. So if you call it T0, it turns out to be about 400 per cubic centimeters. Now that I mentioned it, okay, Paolo will talk about it. And the number of baryons, well, you have to know that number. It's just that there are very few stars in the universe. Of course, there is a lot on a clear sky night, right? But actually the density is small. The number of baryons, or the density of baryons per number of photons, is 10 to the minus 10. It is that small. It's an interesting thing. The universe, however, is supposed to be filled with neutrinos also. That's very interesting, okay? And we'll come back and talk about it when you learn more the dynamics of the evolution of the universe. So the world is made out of this, what the first generation particles are, including the photons. So what are these other generations doing? This is often called an ugly feature of the Standard Model. This repetition. And people complain, even Nicolas was obviously, he admitted it was not his feeling, worrying. How come and why are then the masses so different between these generations? Okay. Remember that they actually play a profound dynamical role, the generations. We have seen how the existence of the charm quark was crucial to give us correct physics, okay, Mason? That was great, okay? It was even invented for that reason, and the mass was predicted. And moreover, we counted the phases in our mixings, right? When we look at the VCKM, which is n times m unitary. And we found out the number of phases is n minus 1, n minus 2 over 2. And this is what Crocking Convention Mascava to say that if you want to have CP violation, there should be the third generation. And there was third generation, okay? This is somehow a remarkable success of the Standard Model. And remember how the argument goes: if I write the weak interaction, which would be G over square root of 2, UCT L. Let's now specify 3 generations, DSB L. Sorry, well, let me write it here to emphasize. What comes in is the CKM matrix, right? Plus Hermitian conjugate, which I can write as UI G over square root of 2 Vij. Let me call this V. Vij UL I gamma mu DLJ. Why don't we include the W boson? W mu plus Hermitian conjugate, which would be Vij star DLJ bar gamma mu UIL W mu minus. This is the weak interaction. Lagrangian, and we said under CP violation, what happens is that this goes under CP DLJ bar gamma mu ULI W mu minus. It doesn't go into its Hermitian conjugate. The Lagrangian does not stay invariant. Okay? So we concluded from here that the CP violation, this was equivalent with Vij. And that prompted the statement that n must be at least 3. Now we
said that the phase for the 3 generations should be physical and be measurable.
Yes, yes, of course. Well, you will measure it in the you know how you do. You measure the mixing angles. How did you measure Cabibbo angle? Where you looked at the decays of cations to pions. You look at the beta decay. You look at the terms that depended on cosine theta and sine theta. You measured it. You will measure the other angles that way, of course, looking at the decays of heavier generations of bound states made out of them, the physical particles. And then you measure the phase by looking at CP violation precisely. So let's say a few words, since you asked. In other words, when I looked at the K long, K short, when this was real, okay, this is the usual DS. Or if you wish, S bar D, D bar S, or vice versa, D entering, obviously, K going to K bar. This, in the limit of P external is 0, gives me the static effective Hamiltonian with delta S equal 2. But that, of course, produces delta and K. Remember, this is what we found out. That was precisely delta mk. Why? When I looked at the matrix kk0 bar, kk bar, this was these elements have to be the same. By the way, this is the measure of CPT. One of the reasons that we believe in CPT, this has been, for example, in the K-meson system, this has been, the mass difference has to be less than 10 to the minus 18. Hello. Congratulations. I heard from, we heard. Very good. This is really, the difference is 0. To a great precision. Much better than the mass difference, okay? And therefore, the difference between K bar masses comes from this off-diagonal mass term. When this is real, this, of course, will give me the eigenstates, which are K plus minus. Remember, we found out K plus K bar minus, properly normalized. Obviously. 1, 1 and 1 minus 1 are eigenstates. Therefore, if I want to have CP violation, obviously this cannot be real. And once it is not real, then the eigenstates will not be k plus k minus, right? If I have here plus I epsilon some m0 minus I epsilon m0, something that splits them, the complex difference, the imaginary piece that is there, that will produce CP violation. And that can only come from the third generation, obviously. If I have only two generations, there is no phase we have seen.
And even for the bigger number of generations, at least one of the phase is real, the others no.
If there was more, you mean if there are 4 generations?
Yes.
You will have 3 phases. And therefore the predictions would be very messy, okay? Because, you wouldn't, in one process, you wouldn't determine these phases.
So all 3 of them would be somehow...
Of course, all 3 would be physical. This is the number of physical phases that we count out. When I say the number of phases, these are the real phases, the physical phases. We use the freedom of the definition of quark masses and got rid of all possible phases that we could. This is what state. There is nothing I can do about it. These are physical phases. It will be much harder to fail, right? This, of course, is impressive that this did not fail. Not only did they agree with the K-meson system, then you can repeat it for the B-meson, you can repeat for the whole system of 3 generations, and you have only one phase. So all the CP violating practices, all the decays, whatever, direct, indirect CP violation, I will not go into detail of this, okay? This is a long and serious study. It works beautifully with just one phase, okay? This is this famous celebrated success of the standard model at low energy. But in order to do that, I have to exchange a d quark here. Of course, the way I parameterize the CKM matrix, okay, the Chow and Kyung, the one that we took, even the Chak-Wonk, when it enters, will have a complex contribution, okay. But if there was no third generation, or if one of the mixing was 0, then this would go to 0. This would be fictitious. Okay, it's coming from here. In any case, remember I argued that there was a surprising fact. Oh, this is very important. We've seen, when we computed this delta mk, we said it has to be proportional to G Fermi. I took 2 generations. Alpha over 4 pi. This was Lazyman's approach. There was sine square delta Cavivo. Let's not add the top quark yet. Let's just think of up and charm. I'm taking cosine theta equal 1. Okay. Sine theta is 1, remember? Because if there is cosine here, there will be sine here. We agree, right? And then we said, if the mass is a 0, or even just a generate, then there is no mixing. You can redefine, you can get rid of the mixing. Or better to say, there will be a cancellation between up and charm quark. One goes with cosine theta, sine theta, the other with the minus sign. We saw it explicitly. So what we got is m charm squared minus mu squared over mw squared. And then we said because of no other scales, this will be proportional to mk cube. It has to have a dimensional mass, roughly. Okay? This is very important, the dependence of on the m up is practically 0. This is what determines the Chak-Wonk mass, theoretically. And this is what agrees with the experiment when you look at the charmonium. The question you should ask immediately, but how come top quark doesn't dominate this? The top quark contribution will go m top square. True. There is also m top square over mw square. But that will be proportional. If I now add a top quark, let's put it here, then this is theta 2, 3, and this is theta 1, 3. And look how the standard model conspires to work. People often argue that theories, there cannot be these conspiracies. That's not how theories work. It's on the other way around, actually. A good theory lives dangerously, and then barely survives. These angles are very small. So this is actually much smaller than this. Because this is of order 10 to the minus 3. And this is of order 10 to the minus 2, maybe a few times. So this is practically negligible. The champ quark dominates completely k long k short mass difference. However, when you look at the CP piece, that will not be true, because without the top there was 0 there. So, these are the things that I keep telling you. You can always ignore CP violation unless you are talking about CP violation. You can ignore neutrino masses. So, you look at the thing where there is physics of masses, then you will ignore neutrino mass. But if you look at the processes where there was 0, then maybe you will see something, okay? And this is how you see the phase. This will be negligible in the real part, which I call delta mk. But if I look at this CP violating phase, in other words, the element, why don't I write it? The element that I wrote, and we won't do this calculation, it's too messy. I think I'll just ask you to do 2 generations, okay? It gets a bit complicated. We'll see. Mk, this is delta mk, which I defined as real. Then there will be a complex contribution 1 plus epsilon. There will be a small, and let's call this epsilon Cp. Epsilon Cp is of order 10 to the minus 3. That's the parameter that measures Cp violation. And here you have delta mk 1 minus epsilon Cp. I'm not sure about that. The important thing is that they are not equal. Or this is a physical mass matrix. The eigenstates are not anymore 1, 1 and 1 minus 1. This will produce it. This will come from the exchange of the top quark. It was 0 there. And this, remember, I told you, has to be proportional to theta 2, 3, theta 1, 3, theta 1, 2. Remember how I argued the other day? We've seen that there was no phase when a particular mixing vanished. You need all 3 mixings to be non-zero. Okay, is this clear, please? This is what we discussed. And I will decide. I don't know. Maybe we'll have a computation so that you guys go through that. We'll see. But I don't want to go now at this point. I want to talk about more fundamental things than this particular
Is it I epsilon
computation.
or epsilon?
Sorry?
I epsilon or epsilon?
Plus epsilon. I think there is no factor of I. And minus epsilon. Because remember, the eigenstates that we call KL, K short, K long, are K plus epsilon K minus plus minus. No. I'm sorry, I can't write like this. The physical states is K short, is K plus epsilon K minus, and K long is K minus epsilon K plus. And this will come from this mass matrix. I'll leave you as an exercise to check that. When epsilon is 0, the eigenstates are precisely plus or minus. Okay, with epsilon they are not anymore. I postpone the details for the time when this is done. I will include it one way or another. Either I will do it in the class or you will have it as an exercise to compute the... you will learn a lot by computing. It's not enough that someone tells you how it goes, okay? To see the intricate aspects of the G mechanism and the CP violation. All I need you to remember that third generation is a must, and that CP violation is naturally small. Okay, I will stop here. And this will explain any CP violating effect in the standard model. You can do similar thing for the Riemanns on physics, and you will find excellent agreement with experiment. Okay. The holy grail of the, low energy physics and all physics is just at the LHC, looking for deviations, improving the experimental findings and hoping that before or later the standard model will give in. We all want to find the road to new physics, okay? So instead of finding this ugly, okay, I would say that there is a beauty in having this extra generation. In a sense, it was invented, extra generations, to give us CP violation. Where you say, well, who cares? Why do I want to have CP violation? What's the big deal about it? Let's go, you were saying to the world, if there was no CP violation, it's a nicer, more symmetric world. There is, however, a dramatic possibility of us understanding the origin of matter. It has a name even, it's called Genesis, it has a biblical name. Okay, it's maybe over-ambitious. I myself have worked with it and I sometimes have doubts whether it's taking us in the right direction, but it offers the following possibility. You see, the universe is very strange. Doesn't matter where you look, I can check that we are both made out of matter. That's already interesting. No, you would expect a more symmetric universe, and then we would have annihilated. It doesn't matter how far you go, no traces of antimatter have been found. If there were big chunks of antimatter, you would expect annihilations. Okay. We can worry about that. So there's an interesting question, why there is just matter in the universe? Or at this large distance, if I look, the solar system is surely made out of matter, right? But the claim is even that the galaxy is made of matter only, that no trace of antimatter has been found. You heard of this possibility? It's called baryogenesis or leptogenesis. Did anybody hear of this? This is not a time and place to learn it, but it goes with the following possibility. Imagine a small digression. Universe was very hot, bless you. Universe was very hot in the past. You and I know that. Do you know how hot? Can you tell me a little more? Very, very hot. Roughly. Why do we say it was hot? What is the physical process that we know that took place? Very important.
Like quarks,
that works.
We
have a name for that.
Plasma of quark and let's say.
No, we have a name for what happened. Nucleosynthesis. You can trace the early universe to the time of nucleosynthesis, so the decoupling of the proton and neutrons that were in the equilibrium. You didn't talk yet about it. Okay. Then let's postpone this again. Let's postpone it. Remind me, please. I should be intrigued. I will show you that the CP violation is an essential ingredient. If I would like, as a physicist, to explain genesis, the creation of matter, in other words, I have to understand the following thing. Imagine that somehow universe started out to be symmetric, which would be natural. Or even imagine that I show you that in many of the theories that we have beyond the standard model, the universe was necessarily symmetric. Then how in the world did this separation took place? Where did the antibarriers go? It's very hard to separate them. What could happen in principle is that imagine somehow that I create a little more, when things are very hot, there is a drama, everything is possible, okay? The way that electron-positron pairs annihilate into photons and photon becomes electron-positron pairs, you can imagine that baryons can become anti-baryons. All kinds of crazy things can happen if there are possible interactions. So imagine that I somehow created more baryons than anti-baryons. Now notice that would require that I break a baryon number. There are theories beyond the standard model that break baryon number necessarily. They're called grand unified theories. So just imagine Okay? So there will be a digression just for 2 minutes, but not a complete one. In that case, I get, I had billions of particles and antiparticles, and I get one little excess of 10 to the minus 10. So I get 10 to the minus 10 more baryons than antibaryons. What will happen? As the universe keeps cooling off, the baryons and antibaryons, those that were equal, will annihilate. And when the temperature is too low, you cannot create them back. So in this scenario, which is possible to imagine, if I can compute that original difference, that would actually tell me why the universe today is so strangely deprived of antimatter. But if I want to create more baryons than antibaryons, then I must break CP. Because if there is a CP symmetry, then baryons go into antibaryons, so I would by definition get more baryons here and more antibaryons there. I could never create a genuine asymmetry. So the CP violation is a must. If we have this genesis, which is often called baryogenesis, okay, which was imagined in 1967 in a beautiful paper by Sakharov, who said, if CP is violated, both CP and charge conjugation, the symmetries that take particles into antiparticles, okay, if baryon number is violated, and if somehow you manage to get out of equilibrium, you don't want to stay in the equilibrium, because in equilibrium everything gets evened out. Okay, he managed to understand an incredible thing, okay, that started a field that has been studied in the last 4 decades, tremendously. Genesis. So the CP violation, okay, I just want to, I didn't expect you to learn anything, but I want you to remember, actually it's fundamentally important for the possibility of having this, even potentially, understanding baryogenesis.
When you talk about strong CP problem, axioms,
I could either at the very last lecture too, if there is time, or if not, if people are interested, I can give you a couple of extra lectures and try to tell you about at least 2 or 3 fundamental aspects of physics beyond the standard model. One is grand unification, the other is the strong CP issue. I wouldn't call it a problem. I don't think there is a problem in the axioms. No, it's not related to this. No, it's something else. And even to mention it, okay, I have to talk about strong interactions, okay? So you can ask me when I finish strong interactions. I just want, sorry.
That strong refers to the strong interaction.
Yes, precisely, because strong interactions are not supposed to violate CP. CP is a very, very good symmetry. It's almost unbroken, right? Only 1 in 10 to the 3 kaons, remember, it would decay wrongly. You don't want strong interactions to do it, but yet it somehow seems that strong interactions like to do that, and that's called the strong CP problem. And I would like to talk about that. That takes us into physics beyond the standard model, so that will be at the very end. All I want you to remember today, that the standard model theory predicted the existence of 3 generations in order to have CP violation. But CP violation may be a mass so that we understand the origin of life. Or actually more deeper matter as it is. So I would say that there is actually a beautiful dynamics in the existence of generations and not a problem. Moreover, as I told you, the Higgs decays, and you are compute into F bar are proportional to Fermi mass squared. And this is how we'll be testing it. So thank God that there are more generations and more of these processes that can give us a high precision test of. The things that you may ask me, so there is a dynamics, deep dynamics, in these so-called arbitrary parameters that everybody worries about, the Fermion masses. They are not just static parameters, okay? They take us to important and beautiful dynamics. What you may worry, as many people do, they say, look, the scale of the theory of standard model is this vacuum expectation value, which is roughly MW. MW is G times V, but G is a number of order 1. I hope you have noticed that. When you write that alpha square is E square over 4 pi. And this is 1 over 137. What is E? Roughly 0.3. It's not that E is small. It's that the actual expansion parameter is E square over 4 pi. We are lucky. E by itself. Okay, alpha is the expansion parameter, not E. G is bigger than E. G is about 0.5. Remember, E is G sine theta double. Maybe even bigger. It's roughly 0.6, I'm sorry. Because sine theta double is a half. So it's not that that this is small. So the scale of weak interactions is 100 GeV. So you can tell me, look, when you have a fermion like an electron, whose mass is MeV, it turns out that actually M up and down masses are also the order MeV. A few MeV. 1 to 10. You can say, well, okay. This is something that you often call the hierarchy problem when there are different scales. You can say, okay, but you tell me, on the 3 level that the guy is like, but then you have to normalize that. Isn't it be natural that because there is a heavy scale, when I do the loops, and I want to correct the electron mass. This question was asked by Weisskopf, by the way, already in 1930. He said, let me look at the loop contribution to the electron mass. And he looked at the photon. And we would, of course, include all kinds of particles, whatever is needed, W, etc. There may be neutrino in the loop with a W, Z, and so on. Right? You and I should agree. Correct? What would you expect without doing a calculation?
Proportional to the expansion.
Okay. Which is alpha. Okay, I'll stick for you alpha over 4 pi. There is no dimension. I need now to stick in the dimension. So let me call it ME1 loop. In other words, it will be ME0. There will be a 3-level result. Then I'm including now this as a loop, right? Alpha over 4 pi, expansion parameter. I hope you meant that. And then, of course, these diagrams are divergent in general. This you're learning from QED. And I could introduce a cut of lambda. So what do you expect? Dimensionally, you would say, oh, this is going to be proportional to lambda. You say, look, I'm lazy. I don't want to do a calculation. A lazy woman's approach. Lazy man's approach. So I do dimensional arguments. This is the scale. Will this go... So you see, I want to postpone these details of CP relation. I have more fundamental things to talk about. More fun, more interesting. Now, the fermion mass in general. What is a fermion mass? It's M fermion F bar F, which is M fermion FL bar FR plus Hermitian conjugate. So you see, when I'm doing this calculation, lazy man's approach, if I get a result like this, that means even if electron mass is 0 at the 3 level, I'm getting that result. Okay? Notice it has nothing to do with the original thing. Now what happens? So let me put a 0 here. This is a 3 level mass. What happens when Fm0 is 0? After all, let me remind you, this all came from Dirac-Lagrangian, which had a kinetic energy minus mass which is I FL bar gamma mu d mu FL plus FR bar gamma mu d mu FR minus MF. I've written this separately left and right to remind you that, of course, the physical original states, the irreducible representational Lorentz groups, are two-component wide spinning. And if there is no mass term, they just propagate freely. Left stays left. Now, we found out, immediately noticed, that the right Lagrangian has a symmetry. F goes into e to the I alpha f. This is equivalent to saying there is a U1 symmetry. For charge fermions, when we describe charge fermions, that of course is a symmetry. That should do with charge. But it's a fermion number in general. Okay. Even a neutral guy would have the symmetry, and that would be the fermion number corresponding to that particle, right? That means that FL goes into e to the I alpha FL, and FR goes into the I alpha FR. Right? This is the symmetry of the Lagrangian. Why? Because the mass term has FL bar FR. Okay? This is the Lorentz structure. But if mass is zero, so if I forget about this term, there is actually more symmetry in the Lagrangian. When n f0 is 0, how much symmetry there is? I remember in the two vectors problem. Oh, I'll come once and I'll have to talk to you a little bit. Okay, we shared it probably, but I'll have to say a few words. Okay, because somehow everybody had failed in there with the two vectors. Okay, and it shouldn't have been that hard, but anyway. But some of you noticed that if I decoupled two vectors from each other, I would actually have more symmetry. O3 times O3. So this is exactly the point here. If the mass of the fermion goes to 0, what you have is a symmetry which is, we call it U1L times U1R. We have a double U1 symmetry, chiral symmetry, which means that I can separately rotate left and right fermion. I can take this, FR goes to FR, and I can take I have two symmetries which don't talk to each other. This is called the chiral symmetry. In the limit, when the fermion mass goes to 0, you get more symmetry. So I'm now inviting you. Imagine now I want to do this calculation. I must say, okay, I want to check whether this is possible. So I will take this to be 0. Can I get this? When I do the loops, what do I use? I use my three-level Lagrangian. So this is an obvious message that I wonder whether you've noticed. You cannot get less symmetry. If Lagrangian has a set of symmetry, you can do 150 loops, you'll always get the symmetric result, because we are using a symmetric Lagrangian. And that's how you're going to check your calculations, okay? You don't want to get results that violate the symmetry of the Lagrangian. Therefore, this cannot happen, because the symmetry tells me that the fermion mass to all loops must be 0. Because if I get a mass, I would violate the symmetry. But how can I violate the symmetry? I'm using the Lagrangian, which is symmetric. That's why I don't have to worry that I will break charge when I do loops in QED. You'll never get a result which breaks charge. You have always assumed that. You will not get results that violates Lorentz symmetry. You don't have to say, oh, maybe at 255 loops, maybe Lorentz symmetry is no good. No, because the theory is Lorentz invariant, and therefore anything that I compute with the theory will be Lorentz invariant.
Because we don't have mass term, but we cover terms that give the mass.
If I have Yukawa terms, I have mass terms. That's not the limit. I'm taking in the limit. When I say the limit that fermion mass goes to 0, that limit is equivalent to Yukawa going to 0 in the standard model. If I have a Yukawa, I will have a mass. After all, M fermion is Yukawa fermion times V. I'm just looking at the limit. I'm not saying that the electron is massless. I'm just reasoning. I'm saying electron has a mass, of course. But when I compute the loop, my loop should reflect the Lorentz symmetry, and it should reflect the charge symmetry. For example, I will not get the mass term between electron and the Higgs scalar. I don't even have to look at that. While this is both charge and Lorentz symmetry, there are no such possible terms because the theory starts with this Lorentz symmetry. And therefore, in the limit that Yukawa electron goes to 0, whatever fermion I look at, the loop should respect the symmetry. Therefore, at this level, and this is what Weizsäcker found out, he found out that he didn't get this. What he got instead, tell me what he should get. Must be proportional to the original mass of the electron, which I called M electron 0. Of course, there is a divergence. It's logarithm. I don't have to write 0 here. I'm doing a correction around one loop correction. In other words, and I'm saying without doing the calculation, but you could do the calculation. Let me summarize more neatly. I'm saying that M fermion, I wrote that the fermion is MF0, the bare result 1 plus alpha over 4 pi logarithm lambda over ME. I have an infinity, but it's a very tiny infinity. Okay, this infinity is negligibly small, if you forgive me a physicist argument. After all, you and I believe that there is a cutoff in nature. Actually, some of you believe even that that cutoff is in form of strings. I don't know what gave you that belief, but I grant you it's possible. But some of you wrote to me that you are actually sure that that will be a way to understand future coming from strings. So you do believe that when you come to the Planck scale, the underlying states of nature are not particles vibrating, but little strings. You see these little strings, which I admire. I don't see them, but I wish we spoke less about the thing that we didn't see any trace of them in 40-some years, okay? As a physicist, I believe that physics has to be natural philosophy, as Newton called it, and Weinberg used this name a lot. So that means that any reasonable cutoff. This is a very tiny contribution because alpha over 4 pi is 10 to the minus 3. Logarithms are small. And this is maybe some number over 100. Put 10 to the 19. You get the number over 100, right? The contribution is small. And this is very important. This is called naturalness, okay? The principle of naturalness that somehow is associated mostly with that Hopf. Other people thought about it, but Hopf made it very clear. That the following argument. If in the limit, when the physical parameter goes to 0, you get more symmetry. That symmetry will protect you to all orders in perturbation theory. You will never get a big result. Right? We say that the fermion mass, and forget even how you got this. Don't even to think of the loops. That is the most general expression you can get. If there is infinity. If there is no infinity, so much the better. So we say that the fermion mass is naturally small. Why is it naturally small? Because the mass will always be proportional to what I said at the tree level. Just like the naturalness of the normalization of charges that stay integers. If you say that they are integers at the tree level, they remain integers. You learn that because of the word identity. What you and I are learning is if someone says that the fermion is light, that's true for all seasons. Nothing will ever spoil that. So there is no problem of form fermion masses. By the way, this is not trivial. For example, if I were to do the same calculation for, say, a scalar particle like the Higgs, what I will get there with coupling 4 pi there would be no protection whatsoever because there is no symmetry. Remember, the mass term came from this. So it's invariant under U1 symmetry that I can imagine, or SU2 or whatever, phi dagger phi. There is no protective symmetry for scalars. So you get this for scalars. Fermion mass is naturally small, but the scalar mass is not naturally small. If you say that some scalar is small, then you have to be clear what do you mean by small compared to what. Now you may have heard this, and I will just say a few words, but you must have heard that people worry about the Higgs mass. Naturalness of the Higgs mass. Hierarchy problem. You've heard these words? Did you? If you haven't heard, then so much the better. Then maybe I don't have to mention it here, but you will hear a lot because this has been one of the central issues in the physics beyond the standard model. There are a lot of people who worry that the Higgs is light. Now you may say you're crazy. What do you mean by light? It weighs 125 GeV compared to what? So people say, well, compared to the Planck scale. I don't know whether we should worry. Compared to the possible cutoffs. You would like the physics of today not to know about the large scales, about the cutoffs that we use. That remember, they can cancel when you do the calculations. You renormalize your parameters, and then the cutoff disappears. Now, in the case of scalars, there is a tremendous sensibility to that large scale. If there is physics at large scale, Higgs knows about that. A fermion cannot know about it. So, bottom line, okay? Well, I can't help but mention it. That for very interesting reasons, well, it's a beautiful field theory. I fell in love with it. Also, supersymmetry became one of the most extraordinary dogmas of the physics beyond the standard model without a single trace of evidence. Right? We keep speaking of supersymmetry. Nobody's ever seen a selectron. I mean, supersymmetry says that if there is U, there is semilio. Okay, for every particle there must be a superpartner. If there is a fermion, there must be a fermion, and so on and so forth. That's kind of interesting to believe without a trace. But anyway, not only that, there has been a deep belief that such superpartners should not be too far. That machines like LHC should see them, and the reason is the following. They're saying, the theory with fermions is natural. Okay? You got this argument, I hope. Small remains small for fermions. For scalar, this would not happen. And when I finish this class, I will say a few words. I want to give you the gap. You have this course on supersymmetry that some of you may take. And it's good to know why you're studying supersymmetry if you're a physicist, okay? And not just algebraic exercise. And the reason is that people said, many people like this idea. if there is supersymmetry, then the fermion and the scalars are basically the same state. Supersymmetry is a symmetry that takes a fermion into a scalar, and vice versa. Therefore, if supersymmetry is good, and fermion is natural, then also the scalar will be natural. Because supersymmetry will take care of that. So, let me just say, right here, I will finish it. There is a chiral symmetry here, which is a protective symmetry. Protective or custodial. Remember when we worried why WZ had the same mass, we found that there was a symmetry, was a custodial symmetry. If we worry why the fermions are light, there is a protective symmetry, which is a chiral symmetry, it's a custodial symmetry. In the limit, when those masses go to zero, they would stay zero to all orders. Fermion masses are naturally small. This you can forget about scalar, this was a small regression, because in the limit m fermion goes to zero, there is more symmetry. Whenever you get more symmetry in the limit of parameter going to zero, then that parameter will stay small. You don't have to worry that perturbation theory can give you a large contribution, okay? Because you could worry the perturbation theory, instead of giving you a small logarithm, gives you a term proportional to lambda. But you cannot do it. I will finish on this note if you don't ask me anything. This is a profound concept, so I wish you would ask me.
So when we have chiral symmetry, then our argument goes that at loop corrections we will have the mass term.
Always. In other words, keep doing this. So in other words, what I'm saying is the following. If you ask me what happens is 255 6 loop, I'll tell you, you'll get alpha over 4 pi 256, and you'll get logarithm of lambda over m. And maybe you'll get some power of this logarithm. I don't care. You'll get a small number. If you wish. You will never get anything proportional to lambda. This possibility of alpha of 4 pi to whatever thing proportional to lambda cannot be there, because you know that this must be zero, because in the limit when the fermion mass goes to zero, you must get zero. Therefore it will be proportional to itself. This is the idea of protective symmetry of small numbers. So if I worry about the strong CP thing that you're asking about, I discovered that strong interactions like to break CP, then I will worry, can I make sure then that there is a protective symmetry that will make this small? That's called, for example, in case of strong CP, these are just words at this point, but since you ask a J-queen symmetry, that requires existence of a particle called axion. It's a beautiful picture. But it's hidden here, the crux of this.
Why can't we follow the same arguments for scalar Lagrangian?
Because you don't get extra symmetry when the scalar mass goes to zero. Write the potential. It goes like this: phi dagger phi plus phi dagger phi squared. This is the interaction, and so on. If I take this to its sigma, I get no more symmetry. It has the same symmetry of my interactions. There is no extra symmetry for scalars. So, another way of saying fermion's mass is protected. Because of this. Scalar mass is not protected.
there is a step between the symmetries we have and the terms we get from the loops.
Yes.
So that step is in field theoretic calculations maybe, and it's very
Well, it's sort of obvious when you do loops, you use your original Lagrangian, the Feynman rules that derive from your original Lagrangian. So you have set of rules, and that means corresponding interactions that respect a certain symmetry. Whatever you do with that with respect to symmetry. You have always assumed that. Otherwise you would be worried, every day you will be talking about, okay, this guy Rajbaz is bugging us day after day with QED, but how will I know? I mean, what, shall I keep on calculating to 145th loop and making sure that Lorentz symmetry is not broken, that gauge symmetry is not broken, that the charge is not broken? No, you're saying because the Lagrangian that he uses has those symmetries. Why did I say this? I wanted to tell you that once again the summary of this is there is a beautiful dynamics in fermion masses, I claim, associated with the Higgs decays and different processes that we talked about. And moreover, there is no problem of small fermion masses, as often people say. Absolutely no problem whatsoever. It is equally natural to have a small electron mass as it is natural to have a large top mass, in this technical sense. Now remember that there is a natural definition. This is called technical naturalness. You say it's natural something that's protected and stays small. There is also a natural definition of a word natural, and that is what happens in your daily life. That is natural for you and me. In that sense, small masses are more natural than big masses because only top quark is carried. All other masses are small compared to the scale, right? Bottom and tau and muon and straight quark, all of them are much lighter than 100 GeV. So maybe the question is, why is top quark heavy? Again, that's not the problem. There is nothing to tell us that the masses have to live at some scale, because the correction will keep that original mass that I took and not the scale that you imagine. Even if you have very large scales, you don't have to worry about that. Well, I have, however, always implicitly assumed, up to now, but then you know that this is not necessary, that there is just one mass type, and that is F bar F. Which I can call, if you wish, Dirac mass. That is the mass term Dirac wrote in the Lagrangian. Not in the chiral form, but who cares? Now remember, we found out that if psi is a spinor, psi transforms into lambda psi, then psi c is also spinor. Right? And psi c is C psi bar transpose. So in other words, there is another mass term, and that is, so let me call this Dirac, Fc bar F. This is also invariant. I'll call it Majorana. This is this. Psi, or F, is UL/UR in our conventions of gamma 5. Psi c is, this is C gamma 0 psi star, so this is I gamma 2 psi star, so psi c is I sigma 2 UR star minus I sigma 2 UL star. Okay, the first homework. I think we did it, oh, maybe. So psi c is, let me write it here, I sigma 2 UR star minus I sigma 2 UL star. By the way, this is also M fermion Dirac, let's call it, which is UL dagger UR plus UR dagger UL in the two component form. Whereas this would be, so this is Dirac and this is Majorana. What is this? I have, this is psi c dagger, gamma 0 psi, so this is M Majorana. What do I get? Gamma 0 is off diagonal, so I am going to get UL transpose I sigma 2 UL. I think there is a minus sign. It's not so important. Notice what the Dirac mass term does. It mixes left and right. Now, we could have guessed that. We didn't need this complicated four component thing, because remember how UL and UR transform? E to the I sigma over 2 theta plus or minus I phi ULR. Rotation boosts. Under rotations they are the same, but under boosts they are not. So if I take U dagger U, I must mix left and right. Okay. This is why the invariant looks like this. F bar F. But what I'm learning that what I always thought, okay, well actually you know it from the exercise that we did, but let's now study the physical implications of that. Let's try to understand deeper what I mean by this. Is the following: if I naively thought that the mass term had to mix left and right fermions, that if I didn't have both left and right, that the fermion was massless, actually was not true. There is a possibility that I even don't have a right-handed particle, and I get a mass term. In the Majorana case, you can have just a by the way, I should add an Hermitian conjugate. The first piece was Hermitian, F bar F, but F C bar F is not Hermitian. And that means that even if I just have a two-component wide fermion, I will get a mass term. So why don't I write this mass term? Why didn't I write this mass term for the electron?
It does not respect all symmetries.
Sorry?
It does not respect all symmetries.
Well, all, don't tell me all symmetry. Which?
U1 will be broken if you have
Which U1?
Charge, electric charge. If you don't have zero charge.
So it's the charge conjugation precise. So this mass term, the Majorana mass term, which by the way sometimes is written like this, psi L transpose C psi L. This will be the same thing, because C has sigma 2, where psi L UL 0. The Majorana mass term is possible only if I have a neutral particle. Actually, Majorana is sort of a neutral. He didn't think of neutrino. It's interesting, all these great consequences, okay, the beautiful physics of Majorana possibility, which means that something will be broken now. You just told me, of course, charge will not be broken, but what will be broken if I have If I have transfer, the associated fermion number will be broken. In this case, we call it a lepton number because neutrino is a lepton. Okay? Neutrino and electron are together in the same weak interaction. So for weak interaction, they're the same particle. That's why we call neutrino a lepton. And W boson cannot distinguish them. So neutrinos. Why not neutron? Why cannot neutron be? This actually didn't work. Neutron is not neutral. Well, it is, but not completely. It carries a dipole moment. You have to be really neutral. You even showed out. You see, what was important was to show that in the Majorana case, you know, the all possible currents would vanish. Okay, the moments, the dipole moments, and stuff like that. You were supposed to. Now, how did it work? Okay, a reminder of the homework we defined. Since I've done all my fine rules in the 4-component notation, I'm not going to now redo everything by this ugly term, right? I don't know what the Feynman rule corresponds. So we introduced a Majorana spinner, which was, remember, if I have a left-handed fermion, I could do this. I could add, this is Majorana. So in other words, psi Dirac is psi L plus R right. If I want to have a 4-component notation, I have to add the right-handed spinner. But notice, this is UL0 plus I gamma 2 gamma 0 no, I gamma 2 gamma 0 UL0. Agree? C is I gamma 2 gamma 0 and psi bar transpose is gamma 0 dagger. Dagger transpose is complex conjugate. So what is this? This is UL0 plus I 0 sigma 2 minus sigma 2 0 UL 0, and this is therefore UL minus I sigma 2 UL star. I can make a 4-component spinner out of 2-component spinner only, because there is a right-handed counterpart, and that's the antiparticle. So we introduced, you see, we found out that there is a possible mass term plus Commission conjugate that violates that particular symmetry, which is a lepton number. Okay, that's equivalent to say that I can create, in other words, this term violates the number of these species. Okay, therefore I can construct a state which is half particle, half antiparticle, because there is no particle antiparticle. It's a very funny guy. It's a hermaphrodite. He cannot decide half of the time. This guy, let's call it neutrino, because neutrino is neutral, so let's imagine that now neutrino, okay, Majorana spinner, half of the time it's particle, half of the time it's antiparticle. Notice, completely crazy, okay? Just half of the time, 50%, okay? Not 49%, 50%. And we found out in your exercise, who remembers, that this Lagrangian, I start with the original Lagrangian, which was I psi L gamma mu d mu psi L minus m Majorana over 2, we had a coefficient psi L transpose C psi L plus Commission conjugate. There is a factor over 2 because there are actually 2 terms. Turned out to be 1/2 I Cyan bar, gamma mu d mu psi m. Open your, if you have minus m Majorana, cyan bar, cyan. Notice that this strange Majorana Lagrangian that I can form just out of two component state. I don't need a right-handed analog. And this is very important, okay? Especially in the case of neutrinos, it's going to be very important because nobody saw a right-handed neutrino, right? So maybe there is not, or maybe it's so heavy that we didn't see it until now. But in principle, I don't need it to write the master. In principle, Majorana told me he actually didn't use the Carl notation. He used the four-component one, just like Dirac used the four-component one. But in our language, it's precisely this. Notice I got the same Lagrangian as Dirac at first glance. So I can use all the Feynman rules that I used before. And we'll do that. We'll work with Majorana particles if they are Dirac particles. We'll have to remember the degrees of freedom when we count. There'll be less particles in a loop and so on, okay? We'll come to that. But the same Lagrangian. The overall factor is irrelevant, right? The Feynman rules do not depend on the overall factor. In the Lagrangian, you can just scale it, renormalize your fields by square root of 2, if you wish. The thing, however, so you are saying, but where is this lepton number violation broken? Here it seems that everything is conserved. Well, it is in the state itself. And Majorana fermions is a crazy guy. Let me actually check my email. Sometimes they like to throw the cards away. I left the card very illegally parked. No, it seems not. Hopefully I find my car. Right? You want to ask a question? Here. You were supposed to show that psi m bar, gamma mu psi m is 0. Actually, it's vanishes. That's not surprising because there cannot be charge carried by this guy carries no electromagnetic current. Okay. The Majorana particle we could show carries no dipole moment and so on. Electric or magnetic moments. It's really neutral Majorana particle. Okay. So neutrino is an ideal candidate, not a neutron. Really, it has to be completely neutral because you see, something will go wrong, even if I try not to couple it directly to the photon, okay, by saying that I have half of that particle, you better carry no charge whatsoever. So, summarize. A Dirac fermion. Notice it has 4 degrees of freedom, 2 plus 2. These are complex spinors which have nothing to do with each other. UL and UR have nothing to do with each other. We group them together because the mass term connects them, but they are actually original, independent states to start with. Okay, this is a Dirac, and this is psi m. You can of course take only UR, and then you will have I sigma 2 UR star up there. Okay, that's just a name that you will give to the states. Okay, so this is Dirac 4 component. And this is Majorana 2 component. And that comes as a surprise when you are very familiar with the wide spinners and so on. The first one is shocking, okay? I know these days one teaches it. I spent years of my life in the 70s when I started to worry about neutrino mass. Nobody talked to Majorana. I was a beginning graduate student and then maybe not so beginning. But even the people that had worried about that, because 10, 15 years before, people worried a lot about the possibility of neutrino with Majorana. They didn't find any physical process that would correspond to that. So somehow it was forgotten. It disappeared. And neutrino was supposed to be massless. And when I was trying to understand the lightness of neutrino, I always imagined it as a Dirac particle. And the issue here, you will see how much more interesting it is if it is Majorana and there is a deep physics, okay? The point is, of course, that we can write one and the same Lagrangian, which is I psi bar gamma mu d mu psi minus m psi bar psi. This is the summary. Whether it's Majorana or Dirac is equally okay. You see why this may be so important. But we have to address the issue anyway, because now that we know that neutrino can have a Majorana mass term, we have to understand whether there will be interesting physics following from there. The second thing is, of course, neutrino is much lighter than the electron. If you think about that, the only guy who knows that they are different is photon. W doesn't know. So the fact that maybe it's Majorana would help to understand why it's so different from the electron. After all, they are like brother and sister, and one is million times heavier than the other. That's very strange. So this would give us hope to have a consistent theory of small neutrino mass. Okay, I went through this again, but you knew it, so maybe that's why you're not asking me much today. But now that I know that nu L is invariant, when I write my standard model, let's not forget about quarks. I talked about quarks and forgot about leptons. Let's forget about quarks. There is no right-handed neutrino, so I said, well, neutrino will be massless. Well, I just learned that it can be massive. So why didn't I write it mass term? Or why didn't Weinberg do that in 1967? He did something else in 1979 that I will talk about. Today there won't be much time. I just said, well, this is invariant. Completely wrong, it's invariant. I'm allowed to write a mass term, so why don't I write it? Remember, I had the same question. I had a question, shall I write this? Why not? Question. And the answer was, it will break sp2 symmetry. It's trivial to see, this is a doublet, this is a simplet. So I can't, it breaks sp2L. Actually breaks also U1 hypercharge, you can see. They have different hypercharges. You can use one or the other. Okay, it's trivial to see. So I'm asking my question, why not? Yes, please?
Again, it's U2.
It will break. How do you see that it breaks SU2? Very good. It breaks lepton number, but who cares? Did you say lepton? No, I don't care. Maybe lepton number is broken. That's not a gauge symmetry. I don't have any problems of breaking a lepton number. Oh, it'd be beautiful if lepton number was broken. Actually, I'll bet you anything that lepton number is broken. I will give you 10 to 1 odds that in near future you and I will learn that lepton number is broken. It's a global symmetry. Global symmetries can be broken. Remember, I have a problem with gauge symmetries because I don't know how to compute that. I don't have a renormalizable theory. Because the interaction of the gauge bosons gets crazy, okay. So you said that the break SU2, tell me, where do you see that?
So they come in doublets, and if it's
This is doublet a doublet, this is not a singlet. Well, you can see, just like T3. It's minus a half plus minus a half. And that's minus 1 of this term. That's not 0. It also breaks hypercharge. These guys carry hypercharge. So I can't write it. Answer. Breaks SU2L and hypercharge. Well, I wrote like this, SU2L. I should have written U1 hypercharge. Oh, I did. So what did I do here to correct this? EL bar ER, remember? I couldn't do it, so what I did, I put the Higgs field here. The neutral component of the Higgs field, if you remember, which was H plus V. Of course, it was not written in a SU2 notation, so I wrote it nicely. I wrote this as QL bar, and then phi, and then ER. No, LL bar. LL is new EL. Okay? But the point was here. You say, this guy is in a doublet. This guy is a singlet. Well, this guy is in a doublet. I could just look at the neutral piece, at this piece, and say, I have to put the neutral Higgs, and then I will write it in a more elegant manner. So if I want to do the same here, I want to start with nu L transpose, C nu L, which is Lorentz invariant. I will have to write, and this is what I call phi 0. Remember the doublet is phi plus, phi 0, right? Q is T3 plus y over 2, and y was 1. So if I want this to be neutral, okay, I just look at T3 and I say, well, this is not good, this breaks hypercharge. So I would maybe, let me try to correct it. Let me try to put the same way that I corrected here. Let me try to put phi 0. Well, it's not enough. This is minus a half, this is plus a half. I'm not getting 0. And let me keep doing it, okay? This is the same Weinberg, 1979, 12 years later. He says, well, I want to see, I want to push it further. Why don't I put another phi 0? You can do that in principle. Notice now that the thing will be okay, the hypercharge will be 0. This is not an SU2 thing, we have to write it in SU2 notation, we can do that in a second. I'm going to stop here. The reason we don't do that in the standard model, why is it that I don't do that? I would have to find the elegant notation for this. Okay, I will do that. But why can't I do that? What is the problem with this? The rule, golden rule, of renormalizability. The dimension has to be 4. Theories with high dimensional interactions are not renormalizable. So when I write this interaction, G Fermi, and then there are 4 fermion interaction, let me write symbolically psi bar psi square. I know this is an effective interaction. This was, remember, this was G square over 8W square or something like this, psi bar psi square. But actually this was not the interaction. There was not 1 over W squared, there was 1 over Q squared minus MW squared. And then I said that Q is 0. I got it if I, of course, include all the dynamics. I propagated W and get the thing, okay. But the original Lagrangian has to have dimension form, and then I may get effective interaction, which are higher dimensions when I integrate my physics out. In other words, if I have physics at this energy and I want to see what is happening here, I'm going to integrate these guys. We say I'm gonna propagate it, but I will say if the momentum is very small, the guy is really so heavy, it just sits there. So that means that here I have to write some scale, call it lambda, or I wanted to write mw for, well, we can write like this, lambda w for Weinberg. This is Fermi operator, which is effective, you know. Okay, it came from the physics. That operator at low energies came from the physics at the energies of 100 GeV when integrate out. So Weinberg says I can write such an interaction. But that, of course, it means it comes from new physics that you and I can call some lambda Weinberg scale. And that scale, lambda Weinberg, by definition, is much bigger than mv, which is mw. So maybe we should put a different name here and not the same w. Okay, it would be confusing. Let's call it neutrino, because it has to have a neutrino physics. I want to emphasize here that neutrino mass is by its definition, okay. I'm learning from the structure of the standard model, the possibility of Majorana mass term. If there is Majorana mass term for neutrino, it's a beautiful window into new physics because it can only come from a theory beyond the standard model. And if you and I can figure out to probe this scale, we will know. This, in a sense, is the holy grail of our field. You and I will know what the new physics is. I will try to understand that, and I stop here. We try to understand that in some lectures, okay, because this is a profound issue.
But are there also models with neutrino being not Majorana but still have mass?
Yeah, sure. 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 We will, you know, I spoke like this. Well, I want to do two things. First, to make it clear for you, the neutrino mass requires adding in your physics. We've seen it. You helped me yourself. You showed me how, without something new, which I parameterize in this Weinberg's manner, I simply could not write a mass term or Yukawa interaction. I couldn't at the dimension 4 term. I may try to play with a group theory here and make it more elegant, but it will always be dimension 5. Therefore, neutrino is massless. Therefore, neutrino mass is necessarily a probe, and that should be. Okay, I want to argue here. I would argue with anybody in the world that this is the window into new physics because that's the only place where the standard model failed. Everything else is working perfectly, and you remember the standard model is the theory of weak interactions. All that it wanted to explain weak interaction as a calculable analogous theory to QED. And who is the protagonist of weak interactions? Neutrino. Therefore, standard model is a theory of neutrino, among other particles, but especially about neutrino. And this is very fair. So among the questions that you and I want to ask is that how would I get such an operator? What could be the new physics? And more important, how would it manifest itself? Is neutrino a Dirac particle or Majorana particle? How would I know? Do you know any process that Majorana will induce? So you know, very good. Alexei talked about it. That has become an experimental holy grail of neutrino physics. There are experiments going all over the world. It used to be proton decay in the old days. And then it came with sand, okay, now maybe the new generation will come, but these days, okay, there are a number of them called Gerda, Nemo, EXO, Majorana experiment also, okay. But unfortunately, it has not been seen. Okay. I've sort of paved the way. Now we have to discuss that physics, and we have discussed how this could emerge and how would I actually approach the issue in the context of the standard model. Any last public question? It's time to eat.